Okay, good evening. Today's lesson is going to be a continuation of what we did. So this is lesson two of two of ideal gases and thermal properties. In the previous lesson, I did discuss about the two gas laws. I'm talking specifically about Boyle's law and Charles' law. We did a lot of stuff on that. So we are finishing up with today's lesson. This will be the last one of this topic. And we are going to look at the relationship between pressure and temperature. And this is called the Gay-Lussac's law. Gay-Lussac's law. That's what you have here. Gay-Lussac's law. So basically, the Gay-Lussac's law states that at constant volume, the pressure of a fixed mass of gas is directly proportional to its absolute temperature. Just give me a second. Yeah, there's a fan making a lot of noise there, so I wanted to shut it off. Okay, so I'm saying that the relationship between pressure and temperature is encapsulated in what we call the Gay-Lussac's law. And it says that at constant volume, the pressure of a fixed mass of gas is directly proportional to its absolute temperature. So basically what he's saying is um, pressure is proportional to temperature. So if we want to get rid of this proportionality symbol here, we can say pressure is equal to K, which is a constant, times temperature. Now, if we want to make the constant, the constant K, the subject of this equation, we divide this by our T here and divide this by T. So this T and T cancel, and therefore we are going to have P over T is equal to K. And so, like we did previously, we can say P1 over T1 is equal to K, and P2 over T2 is equal to K. So, in effect, what we are saying is P1 over T1 is equal to P2 over T2. So this is the formula we are going to use with respect to the Gay-Lussac's law. Now, obviously, in all those laws that I've explained to you, the previous one, Boyle's law, there was an experiment. Gay-Lussac's law, there's also an experiment, just like also the Charles law. So this is the setup, the experimental setup. Of course, there might be variations, but what I want you to establish is that with Gay-Lussac's law, you look for what we call the pressure gauge. The pressure gauge measures pressure. And then there's also a thermometer here. And the thermometer measures temperature. So those are the two key factors, two key apparatus or equipment that you have to look for. Because there'll be a question would answer and they will draw something like this and tell you what kind of experiment or which law is being investigated. So when you are giving like that without any indication, look for the apparatus, the diagrams there. And this one is the pressure gauge, this is temperature, and therefore this is the Gay-Lussac's law. Now, I want to take you back to the Charles law so that you have a close look at it, and then we'll come back to the Gay-Lussac's law. Now, when you go to the Charles law, you will see that, yeah, again, this one has a thermometer. Okay, this one has a thermometer here. This is your thermometer. Okay, where is it rated? Yeah, so this is your thermometer here. Okay, so even in Charles' law, there's thermometer. So the thermometer is not the only thing you look for. With Gay-Lussac's law, you have to look for the thermometer and the pressure gauge. The pressure gauge measures the pressure, and that one gives you. So you don't just see a thermometer and just jump into conclusion and say, oh, that is Gay-Lussac's law. No, thermometer plus pressure gauge. So let's come back to the diagram. Yeah, so we have that. Now, basically, the setup is like you put, this tube in a container filled with water, and then you start heating it. And as you are heating it, the gas inside this bulb, let me show you. Yeah, the gas begins to expand. And when it expands, I told you before that when you increase temperature, you also increase pressure. The molecules begin to vibrate and bounce on the walls of the container violently. So the pressure increases, and the pressure is measured by this. So your thermometer measures your temperature, the pressure gauge measures your pressure. So this is the experimental setup. Anything like this will do. So in terms of the graph, you could draw one like this. You can have your pressure here, your temperature here, but it's absolute temperature. That is Kelvin. And then you have a straight line. It's a direct proportional something. This is, I hope you can see, this is supposed to be a straight line. Okay. Or if you exchange them and you put your temperature here and pressure here, it will still be a straight line that goes through sometimes the center, sometimes it might be somewhere here, but it doesn't really matter. The most important thing is that it's a straight line. It shows that there's an element of direct proportionality in it. So, like we do always, we go straight to trying to answer a number of questions. The beauty about this topic is that it's mainly calculations, and they are generally easy to deal with. Okay, so let's go to the first question. It says that a gas has a pressure of this at a temperature of this. What is what what is the pressure at this? So when the temperature increases, I mean decreases to this, what is the pressure? So you see, say a gas has a pressure of the, so this is P, and this is your T, and this is another T. So they want P. Okay, so you use the Gay-Lussac law, can say P1 over T1 is equal to P2 over T2. Or if you don't want to do it like this, you can also capsize it. It means turn it upside down. So instead of having P on top, your T becomes the numerator, but it should be like that for both sides. So you can say T1 over P1 must be equal to T2 over P2. So you can do it like this or that. Basically, it's the same thing. Mathematically, it is sound. So let's try to fit in uh, the information that we have, and then we'll see how the question is going to be. So your P1 here, let me put this one. P1 is 33 kilopascals. Okay. Your T1 is 50 degrees Celsius. Now, anytime you see temperature, even as we did in the case of Charles' law, you always have to convert it to Kelvin. So this one is the same thing as 50 plus 273. Okay. Converting to Kelvin, you have to add 273. And then you're going to have 273 plus 50. That gives you, according to my calculator, it says 323, okay? Kelvin. Then we come to P2. That is what we are supposed to find. It's unknown. But our T2 was given as 25 degrees Celsius. So again, you have to change it into Kelvin. So you say 25 plus 273. Okay. And that gives you what? 25 plus 273. And that gives you 298. So this is 298 Kelvin. So you substitute it. P1, there's no need to change the pressure into anything as long as the units are the same. So your P1 is going to be 33 kilopascal divided by the temperature here, T1 is this one. So you write 323 must be equal to P2. We don't know. That's what we don't know. Divided by the temperature T2. So this is 298. Okay. So mathematically, you can simply say that we can make this one the subject through cross multiplication. I have always emphasized this whole concept of cross multiplication. You can't do science without learning this. So I have done it before, I have explained it before. So I'll just go straight to the point and say that our P2 can be written as 33 divided by 323 times 298. How did I do it? I made this one the subject. It means this one over 1. Then because of cross multiplication, I can simply take this one up. Okay, it's going to be 33 times 298. That's why they are on the same side, divided by that. So the rest is mathematics. And we are going to say times 33. The answer is going to be, excuse me, let me bring. So this is going to be 9834 divided by 323. Okay, divided by 323. And you should have 30,4 5 kilopascals. Kilopascal. So that becomes your answer. Okay, so we move to the next one. The next one is a more practical example. Let me push these ones down. Okay, so it says that a cylinder, a cylinder containing cooking gas. I mean, those of you who have gases at home, you use gas to cook, you would know what we are talking about. So that's cylinder. So it says a cylinder containing cooking gas can withstand a pressure of this. So this is the maximum pressure. It means that if the pressure exceeds this, it would explode. Okay, but we haven't reached that end of the question yet. It says that the pressure gauge of the cylinder is this at this temperature. Due to a sudden fire in the building, its temperature starts to rise. At what temperature will the cylinder explode? So you are given this one. You can start with this one and this one as your values. So you write the formula there. P1 over T1 is equal to P2 over T2. Okay? You can choose this set as your P1 and T1. It doesn't matter which you really use. It will essentially give you the same thing. So you can say your P1 is equal to 12 kilopascals, and then your T1 is equal to 27 degrees Celsius. I'll just go straight forward, plus 273, because you have to add 273 to it to change it to Kelvin. So 27 plus 273, that gives us 300. So this is what? 300 Kelvin, not degrees Celsius. Then this one is now your P2. So we want to find the temperature T2. So your P2 is 14,9 kilopascals. Then, sorry, P2. So your T2 is unknown. So you simply substitute it. This one is going to be 12 over 300 is equal to 14,9 over T2. Okay? So if you want your T2, you want to make T2 the subject of the equation, effectively T2 becomes, so you take this one there, you bring this one there. So it's going to be 14,9, okay, times 300 all over 12. Okay, so that is simply mathematics, times 14.9. So that gives you 4470 divided by 12. This divided by 12, and your answer is 372.5 K, not degrees Celsius, Kelvin. If you want to change it to degrees Celsius, you subtract it. So temperature in degrees Celsius is equal to 372.5 minus 273. Okay, so minus 273. And then we are going to have 99.5 degrees Celsius. So they are the same. Either you leave it like this, or if they demand that you change it to degrees Celsius, you just subtract 273 out of it, and then you have that. Okay. Now let's move to a real past paper. Now this question says that the diagram below shows the apparatus that is used to demonstrate the relationship between pressure and temperature at constant volume. So you have the setup there. It says that a certain gas is trapped inside the Jolly bulb. At temperature 25 degrees, the gas exerts a pressure of 101 kilopascals. The water bath is then heated to a temperature of 60 degrees Celsius. Write down the name of the law which is studied using the above apparatus. Okay? So it's similar to what I said. So when you see the apparatus, you must check. There is a thermometer here for temperature. And then even though they have not written pressure gauge here, this is your pressure gauge because they've written kilopascal there. So this one is for measuring pressure. And the relationship between pressure and temperature is Gay-Lussac's law. So here you say 4, I'm under 4,31. You say Gay-Lussac's law, something like that. Then you are done. Then you go to 4.3.2. It says that calculate the reading on the pressure gauge at that. So again, you use what you have. You have a temperature of, this one is your T1, 25 degrees Celsius. And then your 101 is your P1. So this one is your T2. And then you are supposed to find what? P2. So let's write it down. We put our formula there. P1 over T1 is equal to what? P2 over T2. So let me go down a bit. Okay. So our P1, according to this, the P1 is 10 is 101 kilopascal. Okay. And the temperature is T1 is 25 degrees. So say 25 plus 273. I think that's 298. Let's see. 273 plus 25 should give you 298. So this is 298. So our temperature T2 here is 60 degrees Celsius. That's what the question says. So we add 273 to it. So 60 plus 273. And that gives us what? 333. So this is 333. This is Kelvin. This is also Kelvin. So we want to find the reading on the pressure gauge. The pressure gauge measures pressure. So that is your P2 here. That is unknown. So we simply substitute it, and then let me we substitute it and say that our P1 is going to be 101. Our T1 is 298, must be equal to P2, which we don't know, divided by T2 is 333. Okay, so if you want to make P2 the subject, your P2 through cross multiplication will give you 298. Okay, 298 over no, excuse me. My mind is somewhere. Let me show you something. Okay, so your P2 is going to be 101 over 298 times 333. Okay, so let me 101 times 333. The answer uh, divided by 298. And that gives us a pressure of 112, comma, according to my says, comma 86. And then you must check the unit well so that you just repeat, you copy the same unit. It's kilopascal, so you put it like that. Kilopascal, and then that is your answer. Okay, so we are done with this. Now we are moving to what we call the combined gas equation. Now, for a fixed mass of gas, you can combine the three gas laws, Boyle's law, Charles' law, and Gay-Lussac's law into what we call the combined gas law or the general gas equation. And that one says that P1 V1 over T1 is equal to P2 V2 over T2. So we have combined them. Now, let me show you something before we proceed. So let me write here Boyle's law, Boyle's, Charles, and then Gay-Lussac's, Gay-Lussac's law. Boyle's law says P1 V1 is equal to P2 V2. Charles' law says V1 over T1 is equal to V2 over T2. And Gay-Lussac's law says P1 over T1 is equals to P2 over T2. So how does this equation here represent a combination of all these three gas laws? You have squeezed them together into one. We call it a combined gas equation or the general gas equation. You have that. So how do we do that? Now look at this very closely. I'm going to show you something. In Boyle's law, temperature is constant. So if we are using this one, let me write it again. P1 V1 over T1 is equal to P2 V2 over T2. So if we're dealing with Boyle's law, temperature is constant. So it means T1 is equal to T2. So if T1 is equal to T2, they cancel out. So this one and this one cancel, and therefore you're going to have P1 V1 is equal to P2 V2, which is the same thing as Boyle's law here. This first one that I wrote, P1 V1 is equal to P2 V2. So we have proved this. Now let's go to Charles' law. Again, let's go to Charles' law. Let's use the same thing. The combined gas equation P1 V1 over T1 is equal to P2 V2 over T2. Charles' law says that at constant what? At constant pressure, okay? So the pressure is constant. It means that your P1 is equal to P2. So if P1 is equal to P2 it means that P1 and P1 and P2 are the same. So they cancel each other. If you do it mathematically, they cancel each other. And therefore the equation becomes V1 over T1 is equal to V2 over T2, which is what we call Charles' law here. V1 over T1 is equal to V2 over T2. Okay? Then let's go to the Gay-Lussac's law. We use the combined equation again. V1 over T1 is equal to what? P2 V2 over T2. The Gay-Lussac's law says as at constant volume, then it continues. So your volume is constant. It means your V1 is equal to V2. So this one cancels that, and therefore you are going to have only this and that, which is the same thing as what you learned before. P1 over T1 is equal to P2 over T2. This. So it means that this formula is actually workable. It's not our imagination. It's a combination, a real combination of all the gas laws. Okay. So when do we use this formula? P1, V1, T1 divided by T1 is equal to P2, V2 divided by T. There's in the previous questions that I've given you, they normally give two variables, okay? Either pressure and temperature, volume and pressure, just two. But when you have three of them, temperature, volume, and pressure, that's when you have to use this equation, P1, V1, T1, because there are three variables there. So we are going to apply that principle here. I think I may have to skip some questions depending on the time available. Okay, so this one says that 250 centimeters cube of hydrogen gas at a temperature of this and a pressure of this. So this is V, volume, this is temperature and pressure. You cannot use any of those gas laws because they deal with two variables. Now you have three variables, okay? So immediately you should know that you are going to use P1, V1 over T1 should be equal to P2, V2 over T2. So here they say 250 centimeters cube of hydrogen gas at this temperature and a pressure of this. Calculate the volume of hydrogen if the temperature is raised to this and the pressure is raised to that. So we are going to put all the information there and then we substitute it. So your P1, and because the variables are many, you have to be very careful you don't mix them up. Okay. Your P1 is 196 kilopascal. Your V1 is 250 centimeters cube. Now, again, with this formula, the only thing that you change is temperature. In other words, the other ones, you leave the units like that. You don't do any conversion. But once you see temperature there, the temperature must be changed. So the volume, we leave it like that. And then the temperature is, T1 is 17 degrees Celsius. So we add plus 273 to it. So here you're going to have 17 plus 273, and that gives you what? 290. So this is 290 Kelvin. So we have finished with the subscript 111. So P1, V1, and T1. Now let's go to the next one. It starts from the next sentence. It says that calculate the volume. So calculate the volume is V2 is unknown. Yes, then calculate the volume if the temperature is raised to this. So your T2 is 67 degrees Celsius, which is 67 plus 273. Okay, so 67 plus 273. And that is what? That gives you 340. Okay, Kelvin. And then the pressure P2 is equal to what? 80 kilopascal. pascals. That is this one here. So we are going to substitute. The substitution is a bit long. So let me write the equation again so that when I'm substituting, you see what I'm writing. So P1 V1 over T1 must be equal to P2 V2 over T2. So P1 is 196. So I write here 196 times the volume. I said there's no need to change it. So you put 250 divided by the temperature. Here is 290. Must be equal to P2. Here is 80 times V2. We don't know it, so we'll put V2 here divided by T2. The T2 is this one. So T2 is 340. Okay. So this one looks long and it might look confusing. What am I doing? Hey, let me try it. So let's substitute it. So how do we make V2 the subject? To make V2 the subject, what you do is that you cross multiply. The same concept of cross multiplication is what you do. You take this one and bring it down here. So you're going to have 196 times 250, okay? And this one here, you can cross multiply them. So you say times 340 because it's 196 times 25 times this because they are all in the same kind of, because this cross multiplication, the numerator multiplies with the denominator of the other one. So it's 196 times 250 times this one must be equal to, times this, then divided by this. You take this one here and then multiply it by this. So this one divided by that is going to be 290 times 80 should give you V2. Okay? And maybe your teacher will teach you a different way of doing it, but this, when I see it like this, is easier. I just move them around. Cross multiplication means this one will come and join this one. So you multiply that, and this one will go and join that one. You multiply that, then you isolate your V2. So the answer is going to be 196 times 250 times 340. The information I have here is 1666 and then 4 zeros. I hope that is right. So 166. Let me clean this thing. This one, there's no margin for error. If you make a mistake, it's going to be a problem because you have to check through everything. So if my calculator is right, this is going to be 166, another 6, and then 4 zeros, 0000. Okay? Divided by 290 times 80. So this one gives me 23200. This is equal to V2. So I'm going to divide it 1666 and then 4 zeros 1, 2, 3, 4 divided by 232 and 2 zeros. Calculator says is calculators. Okay, let me just push this one downward so that uh, according to my calculator, the answer is V2 is equal to 718,10 centimeter cube. So you have to use the same unit as, that's why I say you don't convert the unit. The unit that you used before, this is 250 centimeter cube. So the volume here must also be what? It must also be centimeter cube. Okay, centimeter cube, centimeter cube. So you write that, and that is your answer. Okay, I wouldn't attempt to answer the second question. I think I took a piece of it here. It's supposed to be 150. I would not waste my time to answer it because it's similar to that one. It's almost a repetition of that one. The only difference that I want to emphasize is that it's similar to the previous one. The only difference is that the temperature here is negative 23. So if you want to convert it to Kelvin, you will say 273 plus negative 23. So it's 273 minus 23. So this is all that I have to highlight. If there's a negative value, you subtract. You don't add it like before. Okay. So that's just about it. The other one is the same procedure. You just use what I have done there. There are many other questions that we have to go through. So there's no need to waste my time on this one. Now, this one is a bit of a practical question. And again, that's why I want to answer that. This one says that the volume of an aeroplane tire is that. So this is your V. We can, okay, so this is your V. Let's right there. When in flight with a temperature and pressure of this. So this one is the temperature here, and this is the pressure here, respectively. The maximum volume and pressure are this and this respectively. It means the maximum volume that the tire can be filled with is 250 decimeter cube, and the pressure is this kilopascal. Okay, respect me. The temperature of the tire increases to this during the landing of the plane. Determine whether the tire will burst or not. So this is a very practical question. And it's not every time that they will just give you formulas and then you have to substitute. So you see, you have to think about it. Now, Elena might be confused. Why don't we say this one is maybe V1, T1, P1, and then V2, V2, P2, T2, and then they are confused and say, what are we calculating? Because now we have all the values there. No, you leave this one out of it. Okay, you determine the temperature, and then the temperature you get as your value, you compare it with this one. Is it greater, equal, or less than? If it is greater, it will burst. If it is less than, it will not burst. Okay, so we are going to use the same thing formula. P1 V1 over T1 is equal to P2 V2 over T2. The reason being that in all of them, we have the three variables of volume, temperature, and pressure. So you cannot use Charles' law, Boyle's law, or Gay-Lussac's law. Those ones are two variables. This one, there are three of them. So we use this equation. Okay, we use this one like we did before. So now let's see how we are going to apply it. Your V1. Okay, you can say our V1 for the tire is 200 decimeter cube. No need to change it. Okay, I said with this one, you don't change anything except the temperature. Our P1 here is 300 kilopascal. And our temperature here is 7. So T1 is 7 plus 273, which without using a calculator, we can quickly see this is the same thing as 280 Kelvin. So we have our V1, we have our P1, we have our T1. Now, Here again, you have V, P, and and T, but we don't use this temperature for calculation. If not that, what are you looking for? All the variables are given. So you leave that one out, and then you determine it. Once you calculate it, you check whether it is greater or equal to. So with respect to this, we would say that our V1 is 250. Our V2, sorry. V2 is 250 decimeter cube. Our pressure P2 is what? 3420 kilopascal. And then our T2 is what we should look for. T2 is unknown. That's what we have to find and compare that with what we have given in the question. So we substitute it quickly. P1 is this one here. So I'll write 300 times 200 all over 280. This is your 280 here. Must be equal to your pressure here is 3420. That is your P2 times your volume here, 250 divided by T2. So your T2 is what is unknown. That is what you are supposed to calculate. So to calculate that, you can do cross multiplication like we are doing. In other words, you can take this one up. As it is standing here, is 1 over T1 times that. This is like saying times 1 over T1. So we are not interested in 1 over T1. We're interested in T1. Okay? So we have to make it the numerator so that it stands alone. And to make it the numerator, you take it up here. So all these ones will come here, become the denominator. This one will go up here. So we can say T2 is equal to, okay, we already have this one here. So we'll write 3420 times 250. It's already a numerator here, okay? Now, because we can cross multiply with this, we take this one to join it up there. So times 280 divided by the whole of this one comes down. 300 times 200, okay? Because you see, this one times T2. So if you put T2 here, it's like T2 over 1. So you can multiply it by that. So that is what we have here. And then this one and that. Anyway, depends on how you do it. It's mathematics, so you just have to do it the way you think would work. So with my calculator, I'm going to write 3420 times 250 times 280. And then, yeah, the values are big. Okay, so let's write it there. This is 2394. And how many zeros? 1, 2, 3, 4, 5. 2, 3, 4, 5. Okay. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Divided by this one. It's about 6,000 or something times 60,000. Okay, so divided by 60,000. Okay. Yeah, 60,000, 6 and then 4 zeros. So these ones, 3 zeros will cancel. These 4 zeros here will cancel the 4 zeros here. So you are going to be left with 2394 divided by 6. And when you divide it by 6, you have divided by 6 according to my calculation. It is 3990 Kelvin. Okay. So since your 3, it means that T2 is greater than T1. Remember, uh, sorry. You say T2 is greater than, no, not T1. T2 uh, is greater than 400 Kelvin. Therefore, the tire will burst. The tire will burst or burst because the value here is 400 Kelvin. Look at it here. According to the question, it is 400 Kelvin. This is the maximum. Okay. This is what happens when it is landing. The temperature increases to this. But by virtue of our calculation, this is what we get, which is way bigger than this. So the tire will burst, something like that. So just take that into account so that when you see a question like that, you don't get alarmed. Okay, so we are done with Gay-Lussac's law. We're going to quickly look at the relationship between volume and amount of a substance, which in this case we call Avogadro's law. Now, this law has been indirectly dealt with when we're dealing with the mole concept. We mentioned Avogadro's law. It's on the basis of the Avogadro's law that we have this formula. If you remember something like this, where we say number of moles is equal to volume over the molar volume, something like this. Okay, so it was just derived from here. Okay, so Avogadro's law states that at the same temperature and pressure, the volume of a gas is directly proportional to the number of moles of the gas, or you can say equal volumes of all gases under the same condition of temperature and pressure contain the same number of molecules or the same number of moles. Okay, so we look at what we call the molar volume. Again, we mentioned it during when I was treating the mole concept. I said 1 mole of a gas at STP, standard temperature and pressure. Okay, standard temperature and pressure uh, occupies a volume of 22 decimeter cube. Okay, so I've just drawn a table here. The standard temperature is 0 degrees Celsius or 273. Remember, changing anything to Kelvin, you add 273 to it. So 0 plus 273 is 273. So the temperature is either 0 degrees Celsius or 273 Kelvin. The pressure is 101,3 kilopascal. Okay? And the molar volume is that. Now, in some countries, they also have what we call room, instead of standard temperature and pressure, they use room temperature and pressure. That's why you have the RT, what, and the room temperature is 25. So in South Africa, you don't deal with this. I think it's India and other countries where they deal with this. So I want you to remove this, just forget about this, okay, and focus on only this one, STP. So the STP is 0 degrees Celsius, 101,3 kilopascal. And that is what we are going to use going forward. So the Avogadro formula can also be, summarized like this. V is proportional to N. V is the volume, is proportional to N. So we can say that V is equals, we introduce a constant Kn. So to make the K stand alone, we divide this by N and divide this by N. So we can say V1 over N1 is equal to K, and V2 over N2 is equal to K. So the Avogadro's law can conveniently be written as V1 over N1 is equal to V2 over N2. So that's how it is also written. Okay, like that. So we are done with the Avogadro law. I'm just going to answer a question based on that. It says that a certain mass, a certain gas of mass, what mass is that? No, I think the question is wrong. There's no mass here. I think it's volume. A certain gas or volume, this at this temperature and pressure. A certain gas has a volume. I think it should have written has a volume of this at this and that. Calculate the volume at STP. So you use, because there is V, there is T, there is K, there is P. So you use P1, V1 over T1 is equal to P2, V2 over T2, like we did previously. Except that your P1, according to this one, your P1 is 150 kilopascal. It's 150 kilopascal. Okay. Your V1 is 50 centimeters cube. You don't have to worry yourself and change it. And then our T1, sorry. T1 is 27 degrees. So we say 27 plus 273, which is 300 Kelvin. Then you come to STP. The STP is what you are given here. So you should know what it is. The temperature of the STP is 273. So you say your T2, your let's start with the pressure. So P2, the pressure is 101, comma what? Is this? See the value here, 101,3 kilopascal. So your P2 for the STP is 101,3 kilopascal. And then your temperature is 0 degrees Celsius, which is the same thing as. So your temperature T2 is 0 degrees Celsius, which is the same thing as 273, because it's 0 plus 273. So we're supposed to find V2. But I'm not going to waste my time to calculate, because time is going. We still have a lot to do. We are finishing this today. So I'll just write it down, and then you'll be able to calculate it yourself. So your P1 is going to be 150 times your V1 is 50, all over your T1 is 300, should be equal to your P2 is 101,3 times the volume we don't know, V2, all over 273. So you make V2 the subject. V2 is going to be the subject of the equation. And to make V2 the subject, let me make it easy for you. You still keep your 150 times your 50, those are the numerators, and then you take this one up there, times 273, okay, divided by 300 times 101,3, something like that. So you divide it and you get the answer. I don't have the answer here, so let's move on. Okay, so now we are moving to the next thing, which is, we call it the ideal gas equation. Now, this one is very important. So far, in all that we have been doing, all the calculations that we have been doing, we have not incorporated or included number of moles or the mass of something. So if you have a question where there is number of moles in addition to your pressure, your temperature, and volume, you are asked to calculate something, then you cannot use P1 V1 over T1 equals to P2 V2, because there's no number of moles. The number of moles is N. So there's a new formula or another formula that we use, which says that PV is equals to nRT. Now, when you are dealing with this calculations of this nature, you have to be very careful. Your P is your pressure, and all pressures must be changed to Pascal. If it is a kilopascal, kilo means 1,000. So you have to add the 1,000 to it. You don't leave it as kilopascal. They must be converted to Pascal. Okay? Your volume, if it is in decimeter cube, you have to change it to meter cube by dividing it by 1,000. Okay? This one is number of moles, and this is a constant. 8,31 is called the universal gas constant. It's 8,31. and then your temperature must be changed to Kelvin. So these ones are specific. Pascal, volume, meter cube, your mole, your universal gas constant, and then your Kelvin as your temperature. So this is it. So this question is normally given when there's number of moles. If there's no number of moles, they'll usually give mass, and you know how to change mass into number of moles. Okay, so we have finished with the gas law. This is going to be a summary. I'll just quickly go through it. We have all done all these things, so you should know. Boyle's law is P1 V1 is equals to P2 V2. You know that. Charles' law is V1 over T1 is equals to V2 over T2. Gay-Lussac's law is P1 over T1 is equals to P2 over T2. And Avogadro's law is V1 over N1 is equals to V2 over N2. Then the combined gas equation is P1 V1 is over T1 is equals to P2 V2 over T2. We have done that. Now, of all the gas laws, all of them are directly proportional, directly proportional. The only inverse proportional is Boyle's law. So remember Boyle's law, that is inverse. And they might ask you, what is the relationship between the volume of a fixed mass of gas and its pressure according to Boyle's law? So you say inverse relationship. It means that as one is increasing, the other is decreasing. The others are direct proportionality, and they are all directly proportional. So another question that they have asked, especially in the previous ones we saw, is what is the control variable for Boyle's law? Temperature and number of moles or amount of the substance are the variables. For Charles' law, pressure and number of moles are the variables. For Gay-Lussac's law, is volume and number of moles. For Avogadro's law, is pressure and temperature. And then for the combined gas law, it's number of moles. The number of moles must be fixed. If you change it, then it will not work. Okay? So basically, that is it. So it's just a summary. I'm just going through it before we move into something else. Then we have the Boyle's law. With Boyle's law, you don't do any conversion. With Charles' law, your temperature has to be converted to Kelvin. Gay-Lussac's law, everything remains the same, but your temperature must be converted to Kelvin. Avogadro's law, no conversion. Combined gas law, your temperature must be converted to Kelvin. All other variables can be in their original form. But when you deal with the ideal gas equation, PV is equals nRT, then you have to be very careful. Your pressure must be in Pascal, your volume must be in meter cube, your number of moles or amount must be in moles, your R must be this value 8,83, 8,31, and then your temperature must be in Kelvin. Okay? That is what you do. So we are done with that. Now, but generally speaking, for most of the questions that you are likely to meet, these are the two formulas that you should remember, most of them. P1, they can either come in this format or that one. So these are the two main ones. Of course, the other ones you can create them because, for example, in Boyle's law, like I indicated, if you have P1, V1 over T1 is equals to P2, V2 over T2. In Boyle's law, you say at constant temperature. So T1 is equal to T2, they cancel out. So this becomes Boyle's law. I think I treated it earlier on. So basically it's the same. So these are the two main formulas that you need to know. Okay, so we are going to answer a number of questions very quickly so that you see this one. It says calculate, I think I may have to skip some of them, time is going. Calculate the pressure of, okay, calculate the pressure of this grams of propane gas, this enclosed in this, at a temperature of this. So because there's a mass there, the previous equations, the only equation that is relevant is PV is equals to nRT because that mass is related to number of moles, okay? So this is the only formula. You cannot say P1 V1 over T1 is equals to P2. It's not going to help you then. So this one says calculate the pressure. So we make pressure the subject. So your P is equal to nRT over V, okay? So we have to calculate the number of moles of this one, this N. So we know N is equal to mass over molar mass. The mass here is 70. The molar mass of propane is carbon is 12 times 3 of them, plus hydrogen is 1 times 8. So you are going to have 12 times 3, and that one gives you 36, plus 1 times 8 is 8. So 36 plus 8 gives you 44. So your N, this one, your molar mass here is 44. So your N is going to be 70 divided by 44. 70 divided by 44. And that gives you 1 comma. This one gives you 1 comma 59. 1 comma 59. Okay. So having done that, we have calculated the number of moles, that is N. We haven't finished. We know our R. According to that, it's a constant, is 8 comma what? 31. Our T, the temperature here is 20 degrees Celsius, so you must change it to, you say 20 plus 273. And 20 plus 273. And that gives you what? 293. So this is 293 Kelvin. So we have that. And then the last thing we have to deal with is to convert our volume. Our volume here is 21 decimeter cube. And to change decimeter cube to meter cube, because I said with this equation, all of them must be in standard form. So you can't use 21 decimeter cube like we did with the previous formulas. This one has to be changed into meter cube. So we divide it by 1,000. And you're going to have 0,021 meter cube. So you substitute it. You say P is equal to your N. We write 1,59 times your R, 8,31 times your T, 293, all over your volume here, which is 0,021. Okay? So let's calculate it. We're going to have 1.59 times 8.31 times 293 equals divided by 0,021. Okay, so our pressure is 184,351,41 Pascal. Okay, so you can leave it like this as Pascal. Remember, the unit is Pascal, not kilopascal. Or you can say the pressure is equal to, so if we are changing it to kilo, it means we are dividing by 1,000, something like that. So you move it to 1, 2, 3. So you can write it as 184,31, whatever, and then you put kilo Pascal. Okay, 35141, whatever you should have many decimal places you choose to place it. Kilo Pascal. So you can leave it like this, kilo Pascal, or this. I will prefer this. Okay. So that is how it is calculated. Then we move to the next question. Now this one is a bit tricky. For the next two questions are a bit tricky, but I still think it's important to answer. Now this one says that 3,3 36 grams of a diatomic gas occupies a volume of 2 decimeter cube at this temperature and this pressure. Determine the formula of the gas. Okay. Now, the only diatomic gases in nature are, we start with hydrogen. Okay. Then we have fluorine, we have oxygen, we have nitrogen, then we have your chlorine, your bromine, iodine, and so these are diatomic gases. Okay, they consist of two atoms. So here they say determine the formula. So we are going to calculate and see which one of these gases corresponds to that. So whatever, in order to know whether it is this or that, you need to calculate the number of moles. And then when you calculate the number of moles, you move on to calculate what we call the molar mass. The molar mass will tell us which of these gases is what we are supposed to calculate. So again, this one has mass. So as soon as you see mass, you know that you have to use PV is equal to nRT. Okay? So because I said to determine the formula of the gas, you need the number of moles. So we have to make number of moles as the subject of the equation. So number of moles is equal to PV over what? Over RT. So we leave this 3.36 grams out for now, and then deal with what we have. The pressure here is what? This is let me just go straight to the point. This is the pressure, 150 kilopascal. So instead of 150, we multiply it by 1,000 because this is kilopascal. All the values must be converted to Pascal, not kilopascal. So this is going to be 150, and then you add 3 zeros because it's a kilo Pascal, okay? The volume is 2 decimeter cube. So it's going to be, if you are changing it, you have to say 2 decimeter cube divided by 1,000, so that we change it to meter cube. I said this one you have to be very, very careful. So this one is going to be times 0.002, because 1, 2, 3, yes. 2 divided by 1,000 is 0.002. You have to be very careful with this calculation, because if you miss one thing, you are not going to get it right. Then our R is what? 8.31. Our temperature is 27. So it's going to be 27 plus 273. Okay, and that gives you 300. So times 300. Okay, so let's see whether we got it right. So here we are going to have 1, 5, then 150, and 3 zeros, 1, 2, 3, times 0.002. It gives you something. And then, so when I multiplied it, actually, I got 300 here as the numerator, divided by this one times that. This is 8.31 times 300. And this one gives you 29. This one gives you 29. This one gives you 29. 24, not 29. Let me clean this one. This is something. Let me see how I missed something. Let me just continue. So this one is 2. I will see what happens. 2, 4, 9, 3. Okay. If I miss something, I'll check it again and then we'll do it the next time. But I think I'm on the right path. Let's see. So this one is going to be 300 divided by 2493. Okay, 2493. And that gives you a 0, 120 moles. So that's the number of moles. Okay. But we are not interested in that. We have not finished with that. We are supposed to determine not just the number of moles, but the molar mass. Okay. So we say number of moles is equals to mass over what? Molar mass. So we know the mass here. The mass was given as 3,36. We know that one. So here we can make the molar mass the subject. Again, our cross multiplication can help you make the molar mass. So the molar mass is equal to the mass over the number of moles. Remember, molar mass is capital, mass is small. The mass here is, according to the question, is 3,36. So this is 3,36 divided by the number of moles, 0, 120. 120. Let me use, with this one, it's always good to use as many values as possible, because if you convert them too much, you're going to have a problem. So let's see, 3,36 divided by 0, 12033. Okay. So according to my calculation, the molar mass is 27,9. Okay. So of all the gases, let's go back to the gases that I mentioned. The gases that I mentioned, of all of them, the one that has a molar mass of close to 27 is nitrogen. Remember, nitrogen is 14. So 14 times 2, there are two of them, is 28. So here we got what? 27,9, which is approximately, this is approximately 28. So the gas is gram per mole. So the gas is nitrogen, something like that. Okay. So, uh, so let's move to the next one. Now, this one, let me see how many questions do we have, so that I really want us to, we haven't even gone to ideal gases yet. There's still a lot. Okay, let me quickly try to answer that one. I'll skip some of the questions, but this one, let's see whether, because it's a bit unusual. Okay. It says two gas containers A and B of capacities 4 decimeter cube and 30 decimeter cube respectively are connected by a tube with a tap in the closed position. Each contains oxygen at this temperature and at the pressure indicated in the diagram. So the diagram has the pressures there. You have them in the diagram. Show that the smaller container has 4 times as much gas as the larger container. Okay. So the smaller gas has twice as much gas as the larger container. So the only formula that we can use is a formula that has quantity. Okay. And the formula that has quantity is PV is equals to nRT. Okay. So we are going to use this formula. PV is equals to nRT. And the amount here can only be associated with N. That is what gives you amount, mass, or number of moles. So we make it a subject and say N is equal to PV over what? RT. So for the first one, for the first container, we can say that since it's labeled A, we can say the number of moles is N, and a subscript A should be equal to what? PV over what? T. So what is the pressure there is indicated there 1,5 times 10 raised to the power 6 Pascal. So it's already in Pascal. So we write it 1, see something, 1,5 times 10 raised to the power 6 Pascal. That's what I'm talking about. That is for the A, this one. That is the value there. Times the volume. The volume is in decimeter cube, so we have to change it to meter cube. So since it is in 4 decimeter cube, we divide it by 1,000. And when you divide 4 over 1,000 divided by 1,000, you get 0,004. Okay? Then we divide the whole thing by 8,31, that is the value of R, times the temperature. What temperature is given there? The temperature is 27. So 27 plus 273 is 300. So we are going to have 300 here. So the value of Na, or perhaps let me just pick it from a book that I got it so that it wouldn't waste time. Let me just give you the answer. Maybe let me see. Let's calculate it. This is going to waste time to search for the answer. So this is going to be 1,5. 1,5 times 10 raised to the power 6. So it's going to be, we can make it 15 times 10. So it's going to 1,5. And then we add 5 zeros to it. So 1, 2, 3, 4, 5. Okay. Times 0,004. What is the answer? So this one, the numerator gives us 6,000 divided by 8,31 times 300. And this one gives us 2,493. So when you divide this one, you're going to have 6,000 divided by 2,493. We are going to have our Na is 2,4. Okay? Mole. That is the first one. Then we go to the next one. The next one is NB. So do the same thing, PV over RT. Then we look at the, excuse me, let's go back to the diagram. The P is 5 times 10 raised to the power of 4. So the P is 5,000. Now, times 10 raised to the power is 4 zeros. So 50,000, 2, 3, 4. 1, 2, 3, 4. Okay, because it's 5 times 10 raised to the power 4 Pascal. If you look at the question, yeah, so this is what we have. So there are 4 zeros after the 5. So that is 50,000. The volume indicated there is 30 decimeter cube. So 30 divided by 1,000, because we are changing it from decimeter cube to what? We are changing it from decimeter cube to meter cube. So we're going to have 0,03. Okay. Then we divide it by, so 8,31 times the same temperature, because the temperature is the same in both containers. So the temperature is still going to be 300 Kelvin. So since I would only deal with the numerator, because the denominators will be the same, since the values are the same, 8,31 times 300 will be the same. So I'm only going to deal with the numerator. Times 50,000. 50,000 gives you what? So it's going to be 1,500 divided by 2,493. So divided by 2,493. And the number of moles here is 0.60 mole. Okay? So the amounts, we have calculated them. The amount in the vessel A is given by 2.4 mole, and then the one in vessel B or the container B is 0.6. But the question says that show that the smaller container has 4 times as much gas as the bigger container. So what you do is that when you are giving something like that and they say show that something like this is what you do. You divide the bigger one by the smaller one. So if you look closely here, the number of moles in Na is big, is 2.4. So you'll say Na over Nb is equal to 2.4 divided by what? 0.6. So you can move this decimal place here and move this one here. So it's like 24 divided by 6, and that gives you 4. So your Na over Nb is equal to 4. Therefore, Na is equal to 4 times what? Nb, because you're cross multiplying this over what? This times that should be equal to this times that. So 1 times Na is Na, 4 times Nb is that. So you have proved it. You proved that the amount is 4 times as that, because it show that the smaller container has 4 times as much gas as the larger container. So this is how you prove it. The Na is equal to 4Nb, and that is the. With respect to the next one, it says that the tap is now open and the pressure in each container becomes this. Calculate the new temperature in the cylinders. So with respect to this one, this is what I want you to remember. When you are given containers like that, like one connected to the other, like we have indicated, the temperature is always the same, okay? The pressure is the same. The volume, the new volume, is the volume of the first one plus the volume of, so if this one was 4 and this is 30, so it's going to be 34 decimeter cube. And the number of moles, you have to add them, this one and this one. So you are going to use the formula PV is equals to nRT. The question is saying calculate the what? The temperature. Yeah. Says that the tap is now open and the pressure is this. So this is your pressure now. The new pressure is given. Calculate the new temperature. Okay. So temperature is what you are supposed to calculate. And so you'll say your T is equal to PV over N. That's how you make T the subject. So your P here, if you go here, you will see that the pressure is given as what? 2 times 10 raised to the power 5. Means 2 with 5 zeros. So we're going to put it like that. 2 with 5 0, 1, 2, 3, 4, 5 times the volume. The volume is the combined volume of the two gases. I mean, the two cylinders. Now, that's the total volume that the gas occupies. So it's going to be 4 plus 30. So this is 34. And remember, it's in decimeter cube. So we have to change it to meter cube. So you divide the 34 by 1000. So 0, 0, 3, 4. Let me see. 1, 2, 3. Yeah. So this is going to be 0, 0, 3, 3, 4. And then you now deal with the number of moles. The number of moles of the gases is going to be the combined number of moles, which the first one was 2, 4 plus 0, 6 NaNB, if you recall. So that will give you 3. 2, 4 plus 0, 6 is 3. Okay. Times your R, which is 8,31. So you do that and you get your temperature. I don't know whether we should do it, but I think you can just do it. It's just a multiplication like we did. You multiply this by this and multiply, and then you get your temperature. So let's not waste time on that. This one is, look, there isn't time. We are going into the next. So let's keep this. I wanted us to do it, but it's going to waste time. This one is similar to the gas one, the molar mass one. You do it and then you calculate it and you get, because you are given a certain mass there, you are given the pressure, you are given the volume. So you do the calculation and then you calculate the molar mass. And based on the molar mass, I think the gas is hydrogen. I think the answer is 2. I did the calculation earlier on. I don't know where I left it, but you do, it's similar to the other one. So again, we don't have to waste our time too much. Now, let's try to finish up quickly. We talk about ideal gases and real gases. Now, real gases are the gases that we are used to. An ideal gas is a perfect gas. It's a model gas. It's a hypothetical gas. It means that it doesn't exist, okay? It doesn't exist in nature. It's just a standard that you compare other gases with. So how do you define an ideal gas? You say an ideal gas is a hypothetical gas. If you cannot remember the word hypothetical, just say it's a model gas that obeys the general gas equation, PV is equals to nRT, under all conditions of temperature and pressure. So if they ask you, this is the definition of an ideal gas, try to cram it. So we're going to compare a real gas and an ideal gas. Real gases occupy volume. Ideal gases, the particles do not occupy volume. Okay? Now, at low temperature and high pressure, the gases exert force on each other. That is real gases. With ideal gases, the particles exert no force on each other. Now, during collision, for real gases, collision is inelastic. It means some energy is lost. With ideal gases, no energy is lost. Now, in nature, like I said, in nature, you cannot find an ideal gas. Only 2 gases get close to the whole concept of, get very close to the concept of an ideal gas. And the 2 gases are hydrogen and helium, or helium and hydrogen. Why do we say they get close to the concept of an ideal gas? Because one, they are very small. Both helium and hydrogen, when you calculate their molar mass, is 2. Okay. Helium is 2. If you check the periodic table, excuse me, if you check the periodic table, helium is 4, sorry. Not hydrogen is 2, helium is 4. Okay, so they are very small. They are very, very small. So we say the reason why they are considered as ideal gases is that they are very small and they have weak intermolecular forces between the particles. Remember, the ideal gases here, there's no intermolecular force. So if you have a force that is weak, then very weak, then it is close to an ideal gas as possible. The second thing is about the size, because their sizes are small. So the particles have almost no volume. Okay, remember this one. It says the particles of an ideal gas have no volume. The particles of a real gas have volume. But these ones are very small. So the particles, when you pack them together, their volume is insignificant. If you recall, I made a statement the other day that if you go and buy groceries and then they give you 100 Rand has changed, 100 Rand plus 2 cents. This 2 cents is insignificant. You can leave it with the cashier. You don't need it because it doesn't add anything. If someone asks you, how much do you have? You don't say 100 Rand plus 2 cents. You just say 100 Rand. So if the particles are very small, even though they may occupy a volume, but the volume is so small that it can be ignored. Okay? Okay, so we are dealing with that. Now we are going to look at what we call deviation of real gases from ideal gases. Under what conditions do real gases deviate? Deviate means to move away from real gases. And this is a question that they often ask. At very low temperatures. At low temperatures, the intermolecular forces of the particles are close together, they attract each other, and eventually the gas liquefies. It changes into liquid. Now, when something is a liquid, it's no longer a gas. So that is where the deviation is concerned. But if the temperature is very high, they behave like ideal gases. But when you reduce the temperature until you eventually convert the gas into a liquid, then it ceases to be a gas. Okay, so that's then at high pressure. Now, when you increase the pressure significantly, you decrease the volume, the particles will now have enough, the particles will have a volume that is, significant compared to the volume, or you can say that the particles begin to repel each other. So the volume of the whole gas becomes more than it is expected. So those are the two conditions, and a very low temperature and very high pressure, okay? Now, not these graphs are graphs that I brought up previously, but I said we'll come back to it, so we wouldn't talk about it. So these are the various categories of gases. The various graphs that are associated with the gas laws. Okay, this is Boyle's law. If you plot P over V, you're going to get a straight line. This straight thick line here is for it's for an ideal gas, a perfect gas. Okay. However, we say that real gases behave similar to ideal gases under what? Low pressure. Okay. When you increase the pressure significantly, that's high pressure, there is a deviation. That's why when you get here, you see, so this is the graph of the ideal gas. It comes like this. And the real gas is almost like that one, but when it is moving here, it deviates, it moves away because high pressure. Remember I said here, under what? High pressure. That's one of the conditions of deviation. High pressure, low temperature. That's what you have to put in your mind. So if you are drawing this, you draw the ideal gas equation like this. Then the real gas, when the pressure is high, this is pressure axis. When you increase the pressure, maybe from 0, you are increasing towards the end. When it's going up, it begins to deviate, move away from that. That's why we draw this like this. So when you see these diagrams and they tell you to sketch them, especially multiple choice questions, they can just draw those diagrams and tell you which one is correct. You go for high pressure, low temperature. Okay? So we come to the next one. In the next one, again, is pressure plotted with 1 over volume. We are not interested in volume. We're interested in pressure. So whereas this is a straight line, when the pressure is increasing, so at the beginning, they are close together. But as the pressure is increasing here, it begins to deviate, move away from the straight line. That's why you have the dotted line bending away from that, okay? So again, this is high pressure. When you plot volume over pressure, again, this is the ideal gas one. However, at high pressure, when you are increasing the pressure in this direction, then the deviation occurs. Okay, it bends away from the normal graph. Now, this one is volume over 1 over P. Now, if we had plotted volume over P here, like in this one, okay, if it were like that, then the pressure, the bending away should occur somewhere here, maybe bending away here. But you know that if I say P is equal to 4 and P is equal to 1 over 4, the 1 over 4 is 0.25. So anytime you say 1 over something, it is the opposite of the other. So because the pressure is 1 over P, in the case of here, it's 1 over P. I don't know whether you can see it. So instead of the bending taking place here, it takes place here because it's the opposite. 1 over something is smaller than that thing itself. So it means that the closer you get to this one, that's where the deviation occurs. This one, we'll talk about it in the next section. Then we come to the volume temperature one. Again, temperature at low temperature. So when the values are coming towards this one, that's when the deviation occurs. This is temperature. When the values are coming here, that's where the deviation occurs. It moves away from the real value. Then we come to the Gauss-Lussac's law again. We use the temperature. Here, as the temperature goes here, this one deviates like that. Okay. So we are done with that. Now we are going to look at what we call PV versus P of different gases. Now, if you look closely at this one, I don't know whether you, let me see. Now let me show you what I'm talking about. Yeah, I said this one, we'll talk about it later. So that is what we have drawn here, PV against that. So this is it. Now, if they give you a diagram like this, and then maybe they write here P, V, and then here they write P. Why are these gases showing varying degrees of deviation? This one is the largest deviation. Ammonia, it deviates far from it. This is the ideal condition, is a straight line like that. So this one, ammonia comes down like this and then goes up and then continues up here. Methane, CH4, it bends a bit down and then continues like that. Nitrogen is just up like that. If you had hydrogen and hydrogen and helium, they would be very close to this one. They may deviate like this, but so here would have been for, let's say, hydrogen and helium. They would, helium, He, they would have taken this very close to the ideal gas. That's why we say these ones behave as if they are ideal gases. So the deviation, the extent of deviation depends on two factors, the molar mass and the strength of the intermolecular force. So you start with the strength of the intermolecular force. The one with the strongest intermolecular force deviates far away from the ideal gas equation. So in the case of ammonia here, you know that ammonia, so let me just I have written it here so that you see. With ammonia, ammonia has hydrogen bonding. If you recall, this is ammonia like this, H, H, and then H. And because of the electronegativity of nitrogen, it tends to pull electrons towards itself. So it's delta negative, delta positive, delta positive, delta positive. So if you have another ammonia like this, okay, ammonia like this, you're going to have delta negative, positive, hydrogen is delta positive, another hydrogen is delta positive, and this one will be delta. So there's a hydrogen bond here, okay, between them. So hydrogen bonds are very strong. So because of the strong intermolecular force in the case of ammonia, which is a hydrogen bond, that's why the deviation is very significant. So that's why you have that. Now, hydrogen, every molecule has what we call van der Waals forces or van der Waals forces, as we call it in my country. So in addition to hydrogen bond, you have that. That's why ammonia is the one that deviates most. Then we have nitrogen. Nitrogen has only van der Waals forces, okay? And the molar mass of nitrogen is 14 times 2, that's 28. That one for this one, methane is 12, okay, for carbon, plus hydrogen is 1, 4. So this is what? This is what? This is 12 plus 4 is what? 16. Okay. So And then you have van der Waals forces for these ones, ammonia. So technically speaking, the greater the molar mass, the greater the, the intermolecular force. So that's why you have this one deviating like that, and this one deviating in this way. Now, in addition to that, we also have the fact that ammonia is also, methane is also spherical. So, but again, I have never seen a question of this nature. I just took it from a book and I felt I should explain it. The most important thing is that the deviation depends on the strength of the intermolecular force and the size. The bigger the size and the bigger the strength of the intermolecular force, the bigger the extent of the deviation. Okay, the extent of the deviation. Okay, so we are done with that. Now let's just answer one more question and then we call it a day. Now, this one says the diagram below shows a sketch of product PV against that. Okay, so okay, the diagram below shows a sketch of the graph between PV against P for 1 mole of oxygen gas at this. This is the solid line. The solid line is this one. The dashed line represents what we call the ideal gas situation. So what is meant by the term ideal gas? What is an ideal gas? You say an ideal gas is, you go and define this one. You say an ideal gas is a gas that obeys the formula PV is equal to, you can say KT, or you can say PV is equal to nRT under all conditions of temperature and pressure. That is an ideal gas. So you get that. Then the second one says that exactly 3 moles of a gas, this 3 moles of a gas occupies a volume of this at a temperature of this. Calculate the pressure of the gas at this temperature. Okay, calculate the, so it's the same thing. We're going to have 4.2. You use PV is equals to what? nRT. Okay, calculate the pressure. It means we make pressure the subject. So you say P is equal to nRT over V. So your N is your 3 moles. You put 3 moles here. Your R, you know it is 8,31. Your T is 15,8. You add 273 to it. Then you put it there. Your volume is in 12 decimeter cube. So what do you do? 12 decimeter cube divided by 1,000. And then you substitute it and then you get your answer. I don't want us to waste our time on that calculation because we have done too much today. Then this one says that if the volume of the container in question, this is doubled, what will happen to the pressure of the gas? Rise, increase, decrease, or remain the same? The pressure will decrease because the relationship between pressure and volume is inversely proportional. Remember, this is what Boyle said. Okay, this is what Boyle said. So if pressure increases, volume decreases. If pressure decreases, volume increases. So what if the volume of the container in this is doubled? Will the pressure increase, decrease, or remain the same? The pressure will decrease. Explain the answer in terms of the relationship. That's what I've just explained. So you say, according to Boyle's law, and then you have to check the marks there. The marks is 2, so you have to speak a bit. So according to Boyle's law, pressure is inversely proportional to volume at constant temperature. So if the volume is doubled, the pressure decreases. That's all. So basically, this brings us to the end of today's lesson.